A very good day to Dr. Muhammad Arif. I'm Emma Surya Skoli and we meet again for the last experiment. Together with my teammates Remini Martin and Jimmy Samshir, we will present to you heat capacity estimation and entropy generation. To kickstart, I will present to you the abstract. The purpose of the experiment is to estimate the heat capacity of different metals provided and to estimate the entropy generated when these metals are dropped in a container containing water. To accomplish this objective, the metals are submerged into heated water and left until temperature reaches 80 degrees Celsius. Right after it reached 80 degrees Celsius, the metals was transferred into the second beaker. Then, the temperature of water was recorded for every time interval until constant temperature was reached. From the bar chart that we have plotted, aluminium has the highest heat capacity among the three metals. The experimental value and theoretical value of specific heat is compared to measure the percentage error. Ways to minimize the errors are provided in the discussion. From the result, we can conclude that copper is the best materials compared to aluminium and iron as it has lowest specific heat capacity and average total entropy generated. Next, we move on to introduction. Heat capacity is defined as the amount of heat required to raise the temperature of a mass of substance by 1 degree Celsius. The heat capacity in calories per gram is called specific heat. Heat capacities are measured with variety of calorimeter and using the formula of the law of thermodynamics. The measurements of heat capacity is important to determine the entropys of materials. Entropy generation is the amount of entropy which is created generally during irreversible processes by means of heat flow through thermal resistance and others. Its value depends on the nature of the process and not solely on the beginning and end states. According to the increase of entropy principle, entropy generation can only take a non-negative value. Next, I will pass to Rehmini.
Now, Mary and Martin will proceed with the next part of our experiment 7, which is the theory, apparatus, and also the methodology. Now, I'll start off with the theory. Okay, so in our theory, the amount of heat needed to increase a body's temperature by 1 degree Celsius is known as the heat capacity. As two bodies of different temperature exchanges heat, the amount of heat lost by the warmer body equals to the amount of heat retained by the cooler body, and an intermediate equilibrium temperature is reached. This is true provided no heat is lost to the surroundings. In this experiment, a heated solid with known mass m and temperature is lowered into a calorimeter containing cold water with known mass m2. The equilibrium temperature is then measured. The magnitude of the heat gained by the water must be equal to the magnitude of heat lost by the solid. So below is the symbol configuration and also the equation. So for the equation, heat lost by a solid is equals to mCp bracket T2 solid minus T1 solid. Heat gained by water is equals to M2 bracket Cp times by T2 water minus T1 water. And Cp of water is equals to 4.187 kilojoule per kg Kelvin. Basically, at equilibrium, T2 solid is equal to T2 water. So the configuration, as you can see on your left, is Cp is actually a specific heat capacity in the unit of kilojoule per kg Kelvin, and M is the mass in kg, and T is temperature in Kelvin. Next is the entropy change of a system or its surroundings can be negative. The total entropy the total entropy generation as total is positive. A process must proceed in the direction that complies with the increase of entropy principle, which is Sgen is more than 0. The magnitudes of the irreversibilities present during the process are measured by the entropy generation. The entropy generated during this process is determined from, as you can see, the equation below and symbol configuration, whereby in the equation, the delta of S is equals to mCp ln bracket T2 over T1. And the Delta of S total is equals to delta S metal plus delta S water. So basically, as you can see, is on your left is a symbol configuration. So for the delta S metal is entropy change of metal in kilojoule per Kelvin. For water is entropy change of water for kilojoule per Kelvin, and also for total is total entropy generated kilojoule per Kelvin. So basically, for all the delta S is the your unit will be kilojoule per Kelvin. Now proceed is our apparatus. So in our apparatus, you can see is the diagram which has the first one is our metal string, thermometer, aluminum foil, iron metals, aluminum metal and copper metal. We'll be using three metals in this experiment, followed by beakers, which we have two there. Then we have water and also hot plate as well as weighing scale. Alright, so now I proceed with the methodology. So in our step 1, firstly, each metals are weighed using a weighing scale and their readings are recorded in table 1. Step 2, then 100 milliliter of water was filled in the first beaker. Step 3, once it has reached 100 ml, the water was heated using the hot plate. Next, the copper block was attached with the metal string. It was then lowered into the heated water until fully submerged. Step 5. The copper block was left in the water until the temperature reaches 80 degrees Celsius. Assume temperature of water equals the temperature of metal. Step 6. 100 ml of water was filled into the second beaker while waiting for the copper to heat up. Step 7. The initial temperature of water was measured. Step 8. The temperature of water in the first beaker was measured until it reaches 80 degrees Celsius. The copper block was taken out from the beaker using the metal string and was immediately transferred into the second beaker that contains 100 ml of water. Step 9. The beaker was connected using an aluminium foil in order to minimize heat loss to the surrounding. Step 10. The temperature of water was recorded for every time interval as in table 1 until the constant temperature was reached. Step 11. The water was stirred throughout the process to ensure heat was distributed evenly. In step 12, finally, the experiment was repeated using aluminium and iron block. So that's all from me for the theory, apparatus, and also the methodology. Thank you.
Hi, Assalamualaikum. My name is Muhammad Juhilmi bin Shamse and I will continue the presentation, which is my part is result, discussion and conclusion. So, as a result, we get this as a table 1. So, mass of water is 100 gram. So we do a calculation which is specific heat capacity, heat loss by the metal equal to heat gain by the water, and copper we get 0.6756, temperature of metal in Kelvin which is T1 metal we get 80 Celsius, and we convert to the Kelvin we get 353 Kelvin, and T2 metal we get 310 Kelvin. So we go to entropy change of metal. We get negative 0.0100, and entropy change of water we get 0.0109. Total entropy generated which is 0.0008. And this is a table that we get of metal, water, of copper, aluminum, and iron, and the total entropy. So we go to the discussion. So this is a metal which is copper, aluminum, and iron, which is the theoretical value and experimental value. And copper theoretical value for copper is 0.385, for aluminum is 0.9, for iron is 0.45, and experimental value for copper, we should get 0.756, for aluminum 1.7622, for iron 0.8120, and the percentage error is experimental value minus theoretical value divided by theoretical value, and times 100%, we get for copper 75.03, aluminium 95.80, and iron we get 80.44%. And this is the bar chart of specific heat capacity of metal of copper, aluminium, and iron. So um, the percentage error of specific heat capacity for copper, aluminium, and iron is 75.03%, 95.8%, and 80.44% respectively, according to the table. We may assume that each metal has a large difference in heat potential between theoretical and experimental values. Since entropy generation is an irreversible operation, a system or its surrounding entropy shift may to be negative. It also denotes that energy lost as a result of the work performed. According to the result of the experiment, all entropy change of metal are negative due to heat loss and temperature drop, while entropy change of water are positive for all metal studied. This is due to heat transfer into the water, which causes the temperature to rise. Summing the entropy change of water and metal give the overall entropy produced. We can see that each metal total entropy produced is greater than zero, indicating that the mechanism is irreversible. If the cumulative entropy produced is equal to zero, the process is reversible. If a negative value is obtained, the process is said to be unlikely. So, number one, source of error and method to minimize the error. According to the variation, this experiment may have a few flaws, especially parallax error, which occur when the eye direction is not perpendicular to the scale reading. Other than that, environmental error can occur when the lab temperature is not established and the presence of wind in the lab can influence the temperature of the water. As a result, instrumental error must be considered since the beaker used is not completely sealed, causing the temperature drop to be affected. The thermometer can come into contact with the beaker's foundation, causing the temperature to fluctuate. And To minimize, to minimize the error occur, we can take some precautionary steps, which are make sure the observer eye are perpendicular to the measurement scale of the thermometer to avoid parallax error. The experiment should be handled in a closed environment and make sure that all the fans are switched off. While holding the thermometer, make sure it does not touch at the bottom of the beaker. Use distilled water which contain less percent of impurities inside the medium. Make sure the beaker is insulated perfectly by closing the lid with a rubber band as tight as possible to avoid heat loss to the surroundings. Justification on the importance of stirring the water in the container and justification on the importance of transfer the hot metal quickly into the water. It is important to stir the water with a glass rod during the experiment to ensure that the majority of the heat is evenly spread throughout the water. In this case, the heat transfer rate would rise, resulting in more reliable temperature reading. As a result, if metals are exposed to the environmental for extended period of time, convection between the surrounding and hot material can occur. To stop this, hot metal must be immediately moved into water to ensure that no heat is lost to the environmental. This can also result in a more precise temperature reading due to the low percentage error. It is important to know heat capacity of material and the entropy generated from the heat transfer process. If yes, why? Relate your answer with any possible application. Yes, since material with a lower specific heat potential are ideal for use in cooking instruments such as frying pan, bowl, kettle, and other similar items because they can easily heat up even though just a limited amount of heat is supplied. Meanwhile, high specific heat capacity material are ideal for making kettle handles, insulators, and even covers since a large volume of heat causes just a minor shift of temperature, ensuring that the material does not get too hot. Furthermore, boiling water in a kettle is an example of heat transfer because wherever heat transfer occur, the universe entropy increase. The importance of a material heat capacity and the entropy produced during the heat transfer process is demonstrated in this real-world application. And then we jump to the conclusion. In conclusion, aluminum has the highest experiment value of the specific heat capacity compared with the two metals. Due to the highest percentage of error of all the metal, we have come out with some solution. For example, the beaker need to be insulated perfectly by closing the lid with rubber band as tight as possible. This is to make sure that no heat loss to the surrounding since the total entropy for all metal are higher than zero, it is proof that this process is irreversible process. Thank you.